Okay, so let's start the last lecture from recalling where we stopped last time. So last time we were looking still at our favorite Aztec diamond. And we understood the following thing, that if you consider a section and look at the particles on this section, and this is usually k, and this is n, then what we understood is that these particles form a determinantal point process. Determinantal point process. Do I need to remind someone what is a determinantal point process again? Okay, let's hope no. And this determinantal point process can be described by the following kernel, K, A, and V. So I will specialize immediately all the notations to the Aztec diamond instead of giving you general formula, but it is just a theorem from the last lecture in which you plug in everything that we know already about the Aztec diamond. So the particles have positions lambda I plus n minus I, which means that all of them live in the segment from 0 to n minus 1. And the kernel has a form of double contour integral. And what are we integrating? So there is 1 minus w to the k divided by 1 minus v to the k, 1 plus w inverse to the n minus k divided by 1 plus v inverse raised to the power n minus k. Then there is w to the power b minus k, v to the power a minus k plus 1, and dv dw divided by v minus w. So that's a specialization of the double contour integral formula which we got last time. And the contours, let's be a bit more careful here. With the contours, I will draw you in a picture here. So the singularities of this integrand are at points 0, 1, and minus 1. So these are the points which we should be careful about. And if, excuse me? This is a W plane. It's both. So the plane will be for both variables v and w. So this contour, that will be w, and a bit larger one, that will be v.
Shouldn't we have some w in the denominator and some v in the numerator?
Yes, there are too many. Let me check. So there should be 1 minus w. So no, k is smaller than n. Let me just check. K is this thing. K is smaller than n. Okay, let me check. Maybe indeed there is some confusion between v and w somewhere.
The general formula yesterday, the one that we had from Gorin, the 4 terms were completely crossed. There was a capital H of something.
Yeah, but that's true. But they're still completely crossed, I think, because.
Because W is on the same side. So both W.
No, the W is on the different side because two specializations that we have here. One is alpha specialization. Alpha k is equal to 1, and the h function for this specialization is 1 over 1 minus z to the k. So that's fine. And the second specialization is beta specialization. N minus k is equal to 1. And the function for this specialization is, well, 1 plus z to the n minus k. No,
It doesn't compare directly to numerator and
I think that's actually fine. I mean, according to what I see in my notes, I think that's the correct form. Really, if you plug in.
I'm confused about lambda I plus n minus I is 0 up to n minus 1.
Lambda I plus n minus I, you're not sure whether they change from 0 to n minus 1? Oh. Yeah, it should be k probably here. Because there are k of them. That's right. Thank you. Okay, so now we're starting study of this thing. So we want to concentrate on some part of our picture. For that, we will send n to infinity. K, as before, will be n divided by alpha, where alpha is greater than 1. And the positions A and B, well, A will be some u tilde n. No, I think it's always, n was alpha times k. I think that I always had this notation in previous lecture. I mean, so B is equal to u hat n plus delta B. In other words, now we look near the point which has coordinate 1 over alpha in this direction and coordinate u tilde in this direction. And we zoom in near this point and try to understand something. Okay, if you just plug in, then you can equivalently rewrite this thing in the following form. So that's 1 over the 2 pi I squared times double contour integral times exponent. Yeah, that's the same thing. Because we want, really what's our purpose? We want to zoom in at some point and try to understand what's happening in the neighborhood of one point. So A and B should be near the same point. Okay, now after you do this change of variables, your function can be rewritten in the form n g of w minus g of v times w raised to the power delta b divided by v raised to the power delta a plus 1 dv dw divided by v minus w. And who is g here? Well, g is just a function which you obtain looking into here. So g of w is 1 over alpha logarithm 1 minus w, 1 minus 1 over alpha logarithm 1 plus w inverse. So these are the first term, two terms. And u hat minus 1 over alpha logarithm of w. So that's just, nothing happened. I just rewrote the same formula in different form. Okay, so now we want to address the asymptotic of the integral of this form, and there is a classical method for that, which is called, there are several names for that. Sometimes it's called steepest descent method, sometimes saddle point method. Actually, I like also a lot Russian names. So Russian name is Metod Перевала, which is, if you translate it, something like method of the mountain pass. Okay. Same in French? Okay. Okay, so in general, how do you find the asymptotic of this integral? So let's have a warm-up to understand how you do it. Warm-up is to study a real integral, integral from 0 to 1 of exponent times n f of x dx. And n will go to infinity. Okay, so let's think about this integral. So what's happening with this thing as n becomes very large?
It's easier when you have minus infinity.
Why? What's wrong with 0, 1? I think 0, 1 is fine.
Okay,
I mean, so, yes, exactly. So clearly this is dominated at the points where f is large. Because if f is a little bit smaller, then after you exponentiate nth time this thing, this will not contribute at all. So in order to see the asymptotic of this thing, what we need to find is the maximum of f of x. So we need to find a point where derivative of x is equal to 0, well, assuming that it's inside, as Andrea correctly. Yeah. And then you zoom in near this point, and this you Taylor expand your function in the neighborhood of the point of the maximum, and then that will give you asymptotic of your integral. So that's a general trick. Well, it turns out that exactly the same idea works in the complex case, although the reason why it works is a little bit different, but still works. And so this idea hints us that we need to take a look at their critical points of this function. So the points where the derivative is equal to 0. Okay, so we need to compute this derivative. That's true, that's true. It's more complicated, but nevertheless, the same idea will work. Okay, so the derivative. Yes, exactly. That will be important for us. Okay, so let's look at the derivative. Well, there are 3 logarithms, so you differentiate each of them. You get, 1 over 1 minus w, 1 divided by 1 plus w inverse, and 1 over w here. So you get. So you get the sum of. Yeah. So you get the sum of 3 fractions. So after you, collect all the terms, then the equation that g prime of w is equal to 0 becomes, well, I did it at home, w squared u tilde plus w 2 over alpha minus 1 plus 1 minus u tilde is equal to 0. So this is just, I rewrote this equation, so hopefully I didn't make mistakes. So let's hope so.
You get 3 fractions and you get only a second order equation?
Yes, because well, there are 3 denominators. After you multiply by all of them, you will have a sum of 3 quadratic things. So that will be quadratic. Yeah. So in the end, you get quadratic equation. Okay, now if you look at the discriminant of this equation, and this is twice over alpha minus 1 squared minus 4 u tilde times 1 minus u tilde. Okay, I claim that if you were carefully listening to the previous lecture, then you should already know this equation. Yes, exactly. So this is precisely if you say that it is equal to 0 and then rewrite it in terms of the usual coordinates of the Aztec diamond, then this is the thing which changes the sign precisely when you cross inscribed circle. So equal to 0, that's an equation of the inscribed circle. Yeah, it is minus, but just in imaginative way. Okay, so you can guess that the properties will change depending on the sign of this thing, and indeed the analysis will be completely different depending on the case. So unfortunately, since it is the last lecture, we will not have time to go through all the cases, so we will only consider maybe the most interesting case. Namely, we will consider the case when we are sitting precisely at the point where the change happens. So we will only, today we will only study the asymptotic at this point. Although following the same ideas, you can also find asymptotic here, but just, we don't need it. We don't have time for it. No, the difficulty is similar, in all the cases. So it's completely the same. What? No, not really. I mean, on the level, you get some counter-integral, just that then you identify the counter-integral with some answer. I don't think that's too complicated. Okay, so let's consider the case when we are precisely at the point where this is equal to 0. So that will be our point. Even here? Yes, that's true. I mean, the asymptotic analysis is still not more complicated. I mean, we will see now that it's kind of trivial. So, okay, so then let's call it U star as the root of this equation. Well, it has two roots, so let's somehow specify the one which we choose. So let us say that maybe alpha is actually greater than 2 rather than greater than 1, so that we actually sit here. That really that is a point in the upper part. And also let's say that we choose u which is greater than 1/2. So u star is greater than 1/2. Again, you can see on this picture that clearly there will be 2 points, one here and one here. Well, let's choose one of them. Doesn't matter which one, but let's choose this one. Okay, now you solve this equation. So, so the solution, let's call it omega. Well, that is 1 minus 2 over alpha divided by twice u star. You plug in the root of this equation. In that you get square root of 1 minus u star divided by u star.
Sorry, what's u star?
So u star is the root of this equation. So this is a determinant as a function of u star of u tilde, and we say that discriminant as a function of u star should be equal to 0. And there are 2 of these u stars, so that's how I specified which one we choose. And then for this particular u star, we solve the quadratic equation. Believe me or not, but that will be the solution. And well, what's important for us is that this point will be a point between 0 and 1. So this is between 0 and 1.
And just it to be greater than 1.
Yes, we needed to specify it somehow. So, yes, given this restriction, that will be between 0 and 1. Okay, so in other words, there is a point on this picture somewhere here.
It's easy to believe. Yeah, that something is equal to 0 and it's a square minus something which is positive only between 0 and 1.
I mean, it's not hard. I mean, what do you mean? It's easy to believe. That's about solution of quadratic equation, you know. It's not so hard to check. Okay, so now we will deform contours in our problem so that they pass through these points. Because as you can see here, really you want your integration path to somehow be near this critical point, and that's what we will do in this problem. Okay, so we will have 1, we will have 0, we will have omega, and we will also have minus 1. And let's draw 2 contours. So that will be an omega contour, a W contour, and that will be a V contour. Okay, so first of all, you can notice that it changed a little bit because V was kind of closing here, now it closes there. But it's not important because if you look at the integrand, actually there is no residue in V at infinity. Really, at infinity, when V is very large, then things decay very fast because of that. Yes, but you do not cross. You deform V through infinity. Yeah, we extend V. Yeah, exactly. So we go around infinity. And that's what we get. Now, let us be a little bit more careful at how exactly these things are specified. So let's draw. I mean, we are not allowed to do anything else because V has a. They will both go through critical point. That's true. Yes. They both go Well, we don't want to go them exactly through critical point. We want to have a little bit of distance just because of the v minus w here. But just a tiny distance.
See, that's kind of weird because in the subtle point when you ask that f prime is equal to 0, well, you're asking for it to be a maximum. But if it is a maximum for g of w, it is a minimum for g of v. There is a minus.
Exactly, but if you look here, we have two different contours, and that's the reason. So on some directions, you will have a maximum. On some direction, you will have a minimum.
So in the W, you have a maximum, and in the V direction, you have a minimum. And when you take a negative, you have a maximum.
Yes. So my claim will be that we can specify these contours more carefully in such a way that exactly along the W, real part is maximized here. So re G of W is maximized. Yeah.
This is just intuition.
And real part of G of V is minimized here. Minimized. No, that's correct. So this is minimized, so with minus it will be maximized. So I want this G along the red contour to be maximized here and along the blue contour to be minimized here. Yeah, exactly.
Yes.
I just want to say that it is minimized along the blue contour and maximized along the red contour.
So minus g is minimized.
Yeah, minus g.
No. It's G is minimized. I mean, so you have a function of G as a function of the contour. Now this function attains its minimum at this point.
G is a function of the complex plane.
Yes, but I want to consider only its restriction to this contour. We don't care about complex plane. We only integrate on this contour.
Yeah, but locally you are moving in the imaginary direction. In both
No, they're not moving in the imaginary direction in either part.
No, you're moving at 60 and 120 degrees.
Yes, exactly. So,
cubic singularity.
yes, exactly. So that's a cubic singularity. So we will be moving under 60 degrees angle.
Yeah, okay.
So if you want to be more careful with these contours, what you can try to do is to draw some additional lines. I will draw them in this color. You don't understand what?
I don't understand the claim. You write once the real part of g of something is maximum, then it's minimum.
Yes, but I mean here that it is minimum along the contour. Along the contour. So when you restrict function, on the red contour, then it is maximized. When you restrict on the blue contour, then it's minimized.
And there are still two other directions in which you have.
Well, there is another direction here.
One going to one.
So
The x-axis is.
So it might become a little bit more clear if you draw 3 additional lines here, which are in violet. And these are the lines where the real part of G of Z is a constant. So these are level lines of the real part, and which all start from the omega. Now, since omega is a double critical point of your function, because that's how we chose it, so that it's not only that G prime is 0, but actually also G double prime is 0. That's because our equation had a double root. So we have both G prime of omega is 0 and G double prime of omega is 0. So that's a double root. So locally, your function looks like a Z cube. And because of that, there will be precisely 6 level lines of the real part going out of this point. Now, there is something you need to be a little more careful to understand that they really locally look like that. So one of them encompasses 0, another one encompasses 0 and minus 1, and another one goes around 1. But it is actually quite easy, so I will not go into that. You just check the signs of this real part at these points, and there is only unique configuration of everything, which can work out. Now, since this is something where real part is equal to constant, and since this real part is a harmonic function, what you automatically will have that between two of these level lines, the sign of the real part, the sign of real part of G of Z minus real part of g of omega, the sign of this thing should be the same everywhere. Yes, because that's a harmonic function, so its maximum and or minimum should be attained, at the border. So the only the only option that you can have is that that will happen there. So because of this, well, here, like everywhere, the real part will be smaller than the real part at this point, and then automatically that point will be a maximum. And in the next region, you will have the opposite thing. So the real part everywhere is actually larger than the real part at this point, and so you will have this property. So this is just analysis of this function. So there's nothing complicated. If you wish, you can draw this graph of this function on the computer and convince yourself, or with some simple arguments. Okay, now notice that if we have these properties, then the same idea as works here also works in this case. Namely, as long as you go outside a small neighborhood of these points, the integrands will decay exponentially. Yes, because the real part is much smaller, so this thing have small real part, and you multiply by n, so it decays exponentially, and the integral dies out. So the only thing that we need to consider is what's happening really in a small neighborhood of this point, and that will give us our asymptotic behavior. Okay, so let's make a change of variables to see this asymptotic behavior. So the change of variables will be as follows. So this delta A will be equal to a hat times n to the 1/3. Delta B will be equal to B hat times n to the 1/3. And we will also localize new variables. W hat will be equal to n to the 1/3 W minus omega, and V hat is equal to the n to the 1/3 V minus omega. So how did this n to the 1/3 appear? Well, it's very easy to see. This is just because we have n here multiplied to something like z cubed. In order to make this finite, you really need to rescale this z by n to the 1/3. And then n times z cubed will become something finite. And that's precisely the scaling that we do here. Okay, so you plug into your thing. And let's write it somewhere. So this becomes, first it becomes 1 over 2 pi squared double integral of the exponent n times rho over 6 v minus w minus omega cube minus v minus omega cube times omega plus w minus omega raised to the power L tilde n to the 1/3. And then there is omega plus v minus omega raised to the power b tilde n to the 1/3. Yeah, just the opposite. It should be a here and b here. A tilde n to the 1/3 a tilde. So this is a third order expansion. So I say that, let's suppose that rho is a third derivative at omega. So it's not hard to check that then rho will be smaller than 0. Just some check that you do here directly. And then, that is just Taylor expansion. So you Taylor expand your function near this point, you get this third derivative divided by 6 times this thing. So this is the first step when I just plugged in delta A, delta B. Then I also make this change of variables. Okay, I forgot here dv dw divided by v minus w. So after you do the second change of variables, you get n to the minus 1/3 divided by twice pi I squared. Now, in this part, you just plug in your change of variables, and you get cancellation with this n, just as you wish. Like here, you need to be a bit more tricky. So you need to factor out the large power of omega, like omega to the power b hat n to the 1/3. After that, you will get 1 plus omega minus plus w minus omega divided by omega. And this will be a small thing. So you will have 1 plus small thing raised to the large power, which asymptotically will become exponent. Okay? So you will have, well, these prefactors are still there. Omega a tilde n to the 1/3 divided by omega b tilde a tilde n to the 1/3. And then what remains is exponent of rho over 6 times w tilde cube minus v tilde cube times exponent of b tilde w tilde over omega minus L tilde V tilde over omega dV omega dV tilde dW tilde divided by V tilde minus W tilde. And something else is missing. There is also another omega here. So just plugged in the things. Nothing happened. Now, one thing which is a little bit suspicious here is this factor. Because there is this omega raised to the huge power divided by omega raised to the another huge power. And the power should be A and B in both parts. But luckily, we can actually ignore this factor. Namely, if you think about the correlation kernel, we don't care actually about the correlation kernel itself. We care about determinants built out of this correlation kernel. Now, in any determinant which is built out of correlation kernel, if you multiply by some function of the first variable and divide by the same function of the second variable, in any determinant it will cancel out. So it's the same as conjugating your matrix with diagonal matrix, so the determinant does not change. Because of that, this factor we can just remove. The correlation functions do not depend on it. Okay, so this is what remains. So there are still some free variables here. You can see that there is some rho here and there is some omega here. And there is scaling everything. You can get rid of this rho and omega. So let's get rid of it and then write canonical form of this kernel, which you get at the limit. And that will be called Airy kernel. So Airy kernel will be 1 over twice pi I squared, double integral of the exponent minus v cube over 3, w cube over 3 plus v cube over 3 times exponent of b tilde w minus a tilde v dv dw divided by v minus w. And here, so what's happening with the contours? Well, if you look here, what were the contours? So one of them was going in this direction. Another one, after you go through infinity, is going actually in this direction. Well, you can make you can make change of variables. So you can also rescale A and B. So let's not call it this thing. So if you rescale A and B and you also rescale the variable, then you can get rid of both things. So the contours in the end will look like that. You will have a complex plane. And you will have a W contour which looks like that, and a V contour which looks like that. Okay, and let us state the theorem that we obtained so far. So the theorem then becomes the following one. Can I erase this? Somebody wants to stare at it for another second?
So what is happening is that when you zoom, you're also having a gap near to omega, or that's just for the drawing?
What do you mean by? Yes, you need to have a small gap just because v minus w. You want these things to be still non-zero.
But do you optimize it from a certain point? Or
No, it doesn't matter. Well, it should be of the same scale. So it should be such that after we zoom in, this gap remains finite. The actual size of this gap is not important. Really, the integral is, that's an integral of complex functions. So you can move it a little bit and it's still the same. So it doesn't matter. Okay, so here's a theorem which we reached. Theorem. Which says that if you look at the positions of these particles, enumerate them in the form that it starts with the largest one and then the next one, etc. So that's the particles in row K. In row K. Then what we establish is that if you look at these particles and you subtract from them some u star times n and you divide by some constant times n to the 1/3. Well, constant is kind of explicit if you look carefully at all these, omegas, rhos, etc. But, if you don't want to mess with it, then you can just write it as a constant. Then this converges to the Airy point process. Which by definition is a point process with a kernel given by this double contour integral. Well, it's important that the integral should be convergent here. So look here, there is w cube and v cube. So this particular direction is good because if you are here, then after you cube yourself, you still go in positive direction. And then it is with minus, so it's good. So the exponent will die. And similarly here, after you cube v, you go into this sector. So you go into the negative real part. And it is good because that's with plus, so it still decays. So that's the only restriction. You need to make sure that the integral is well defined there. Yeah, that's true. So often people use alternative form. First of all, does anyone need any more comments about the statement of the theorem? So I believe that we have proven this theorem. So if you disagree, then please raise your hand and we will try to discuss it in more details. Okay, let's assume that those who are interested agree.
How far away, so L1, L2, L3, if you take the first 5 ones, 7 ones, it's airy. How far away can you go and still see airy?
It's unclear. I mean, I think that you still need to go finite direction, for finite distance.
So it's not like GUE, I think you can go square root of f, right? Or
No, it's unclear. I mean, if you will look locally, then you will see sine kernel quite fast. So here, similar here, if in the Airy point process, if you go far away in minor tensions in negative direction, then this will become just sine process as soon as you go any macroscopic distance away.
So there is no transition?
There is no transition. I mean, Airy itself is a transition. You can think about it. No, I don't think there is intermediate between Airy and sine. At least I don't know it. Yeah, altogether, so all of them. So you think about all of them, but the convergence is in the sense of finite dimensional distributions, of course. Yes, but that's true. That's, you need to be a little bit more careful. You need also to make sure that in this Airy point process there is actually the last particle, which is a property which I have not established. So, in principle, it could have happened that the result, this Airy point process, this doesn't have this structure. Like there is the rightmost point and the second point, etc. But look here, we were careful with what exactly we are doing. So alpha was greater than 2 and u star was greater than 1/2, which meant that we are here, and then the frozen region actually means that up to some point you have no particles. That's how the frozen region will look like. No, it is because the border of the frozen region is precisely the position of the first particle. So here the frozen region will be different. Here they will be densely packed. But that's why we have chosen alpha greater than 2, just to avoid it. Okay, so people often use alternative form for this airy kernel. Let me write it down also.
So in particular, this formula becomes just wrong once it starts to predict a density of particles which is higher than 1.
This formula does what?
Well, this formula is fine as long as you look at at scale n to the 1/3 from here.
It becomes wrong before it gets to density higher than 1, most probably, but for sure it will become wrong at the point.
Yeah.
The density of particles in the original particles higher than 1.
I mean, the formula is still kind of true. I mean, if this formula you can start sending your guys to infinity, like A and B. And this will converge to the continuous sine kernel. And similar to the original model, if you do a limit transition there, it will also...
corresponds to a double point and your airy kernel to a triple point. But when the double point is, the triple point is almost, when the double point is very close to being a triple point,
Yeah,
there's no transition, really.
No, there is a transition. There is a continuous sine kernel.
Yeah.
So here you will have discrete sine kernel, so you will be still on the lattice. Now, when you approach the border, discrete sine kernel will become continuous sine kernel, and the density will be going lower and lower until it finally becomes 0, and you see area. So that's how it looks.
You cannot tune the distance between the
Well, I understand your question, but I think that no. I mean, maybe you can try, but when I know I think that it's impossible, but. Yeah, I think that there is no other intermediate regime. So, alternative formula is a reason why it's called airy kernel. So let's call it proposition, which tells that airy kernel is equal to the integral of x and y is equal to the integral from 0 to infinity of airy x plus t times airy y plus t dt, where what is this airy? Well, that's a classical airy function, which is usually defined as a solution of the differential equation that d dx square of the airy function is equal to x times airy function. So since it is a second order equation, in principle it has two linearly independent solutions, so you need somehow to specify the one you choose. Well, we can even specify here by an explicit formula which says that airy function at point x can be computed as an integral of the exponent v cubed over 3 minus xv dv, where you need to integrate over such contour. The 0, and that's the contour of integration. Well, you can integrate here, but then it will be the integral will be not quite well convergent. Well, it's kind of convergent, but not. Yeah, again, you can deform if you wish. Okay, so this is the classical function, and the kernel can be expressed in terms of this classical airy function. Now, the check is really immediate as soon as you know this formula for the airy function, because you just plug in it for both function, one airy function, another airy function, and you see immediately the appearance of two contours, as we saw there. and this integral with respect to t, you will be able just to integrate explicitly under the sign of the integral. So I will just even not give a proof. It's just direct computation using this formula. Yeah, v minus w in denominator will appear when you integrate with respect to t here, just because you will have one shift and another shift, and the exponent will integrate and produce something in denominator. So that's how it appears. Now, the law of the first particle in the Airy point process, so A1 first particle in Airy point process So what do I mean by first particle? Really, if you look at this Airy point process, then the way it looks is that there is a particle, then the next one, next one, next one, and then there are infinitely many of them to the left, but to the right there are only finitely many, and there is the rightmost one. So the distribution of this rightmost one also has a name that is called Tracy-Weedham distribution. Law Tracy-Weedham distribution. So if you want to compute something about this Tracy-Weedham distribution, then typically you just try to reduce your question to a question about Airy point process. Because actually the best description of the Tracy-Weedham distribution is a description through this Airy process. So suppose that you want maybe to ask about maybe probability that your Tracy-Weedham random variable TV is smaller than some number s. Now from the definition, can we reduce this question to something about our Airy point process? Exactly. So this probability is the same as probability that there are no points in S plus infinity in your Airy point process. This is really just the same event. If the rightmost point is to the left from S, it means that to the right from S there are no points. Just the same event. And this thing you can compute. So one way to write the answer is to write that there is a determinant of the identity minus Airy kernel x and y as an operator in L2 S plus infinity. So this is fancy writing, and it is called Fredholm determinant. But what it really means is that now, how do you really compute the probability that there are no particles somewhere? You can use inclusion-exclusion principle there. So you start with integrating the first correlation function. Well, you integrated too much, so you add back the second correlation function with some coefficient, then the third correlation function, etc. And then when you write that these correlation functions are determinant of this matrix K, you get some expansion. And that's just a fancy symbol which just means this expansion. So just computing this probability by inclusion-exclusion principle, nothing else. So in particular, as a corollary of what we obtain, corollary is that the fluctuations of the boundary of the frozen regions, boundary frozen region, well, they converge to the Tracy-Weedham distribution. Okay. Any questions about this statement? Because we will.
In fact, you have an analogous expression even in exact.
Again?
Without doing the exact thing. So when you had the exact contour integral with the rational function, you could have written probability in a point above.
Yeah, but it will be quite complicated. I mean, you could. There are different methods how to do it, I would say. So just from the expression with the contour integrals, it's hard to understand. People know how to start with this kind of expression, but then find some difference equations for that. And in these difference equations, you can effectively start solving. And then you can, for example, draw a graph of function or something like that. Just from the contour integral there, it's not so clear how to do it. OK, so what you can see is that in this argument, we really didn't use much. So the exact form of the function g, which we will take a derivative, was not important at all. Because in the end, we just concentrated near a single point where it looked like a z cube. Any function would have that. So the features are not important. So, and this is indeed true. So the argument is very robust. So if you apply it to other Schur measures, the outcome will be the same. Or some other measures for which correlation kernels are still given by the double contour integrals, you always can apply this machinery of steepest descent and give this airy point process there. So, in practice now, suppose that you want to find some nice systems for which you will also find, Tracy-Vadim distribution. So how do you do it? Well, there is no nice answer, but the general technology which helped to analyze several of very interesting systems was to find some nice coupling. So if you want to go further, you find a coupling. So what do I mean by that? Well, if you want to study not only Aztec diamond, not only of Schur process, but maybe something more complicated. I will give examples in a second, what kind of more complicated things. The general idea that if you have some interesting system, that maybe you try to couple it somehow with a Schur measure, and then OK, but I know how to analyze Schur measure, and then this will give you understanding of your thing. Well, if you think about it, even in Aztec diamond, we did the same at the very beginning. We didn't know the Schur measure at the very beginning. It was just a problem about dominant tiling, but we found a coupling. We found identification it with a Schur measure. And the very same idea works over and over again and produces many theorems of the same flavor about convergence to the Tracy-Vadim distribution for different systems. So in the remaining 1 hour, I will try to give you 3 examples of the systems for which this can be done. I can tell you the names already. So one of the systems will be TASEP, total asymmetric simple exclusion process. The second system will be longest intrinsic subsequence in permutation. And the third one will be stochastic 6-vertex model. Stochastic 6-vertex model. But somehow the idea will be always the same, that what you need is to somehow couple your thing to the Schur measure, and then you get formulas, you get a method. OK, so let's start with the discrete, with TASEP. So let's erase something. Do you think it's time? Yeah, that's a good time. Let's make a 3 minutes break. And then we'll start discussing these things. Yes, that's true. There is extension. So we only study Schur measures here. So if you extend to multi-line as a Schur process, there is still similar double contour integral formula. And all the arguments go through.
Okay, it's just a few of the powers that are...
Yes, exactly. Just the powers are a little bit different. And you get similar double contour integral with some additional factors taken into account, different coordinates in this direction.
And so there is the new special thing that happens when you are tangent to the zero, because it becomes children instead of 1/2 or something.
Well, in order to get the limit, you will need to rescale in this direction by n to the 2/3. That's true. And then in the end, you will get a new kernel, which will be kind of extension of this one. That's the nature of the additional factors will be such that they dictate that that's what you should do. Let's erase maybe something.
So this is the
are having rational functions of the eddy current.
Well,
In the original experiment, the integral was rational.
Oh, probably the simplest one is longest inclusive subsequence because you don't have 1 plus w.
well, there is no rational. It's not rational. I mean, there will be exponents. So you can say that it doesn't qualify as being rational.
But if you want to have
Still, there will be. Okay, yes, that's true.
which only use rational functions,
But yeah, it's even simpler with
Yeah.
plus one.
Okay, let's think what we can erase. Let's erase this thing. Okay, so 3 minutes are over, so let's start, or let's continue further. So that will be the first system that we will discuss. That will be discrete time total asymmetric simple exclusion process. So for this system you have a lattice of integers, and on the lattice of integers, well, you put particles somewhere. That's one particle, another one, third one, fourth one. And what will be always happening is that we will have only finitely many particles far away to the right, but to the left, in principle, we can have infinitely many particles. It will not be important. Now, there will be a discrete time.
You can have infinitely many holes on the left.
Well, in the end, it will not happen, but you know, when defining the system, you can say that it might happen.
But in your case, it will not.
Yeah, in fact. Yeah, exactly. So in fact, in fact, we will not. So the dynamics is very simple. So it is in discrete time. Now, at each moment of time, each particle checks if there is something to the right of it. So this one checks, while there is something to the right, then nothing happens. So if there is a right neighbor, then do nothing. Well, if there is no right neighbor, so maybe this particle, it looks okay, there is no right neighbor, very nice. Then in this case, you flip a coin, just a fair coin, and if it comes heads, you jump to the right. If it comes tails, you don't jump to the right. So no right neighbor. Flip a coin, jump if heads. And all the coin flips will be independent, so each particle doesn't care about other particles. Okay, so that's a very simple dynamics, and it's called discrete time total asymmetric simple exclusion process. This do nothing, that is what's called exclusion, because that's a case where you don't do anything. Now we will start it for the specific initial condition. So at t equals to 0, we will have what's called step initial condition. So step initial condition, it means that well, let's fix that there is 0 somewhere. And then you say, okay, to the left from 0, everything will be densely packed with particles. And to the right from 0, there will be nothing. So particles packed to the left from 0. Okay, now in this case, you can clearly see that the particles can be enumerated. This is the first one, second one, third one, etc. And then a theorem which holds here, which is due to Kurt Johansson, tells you that if you take the position of the particle number t divided by alpha at time t, well, alpha should be, I don't know, greater than 1, I think, again, and subtract from it some constants times t and divide by some other constant times t to the 1/3. Again, all these constants are absolutely explicit. I just don't want to bother you with writing it down. It's not too important for us. Then this will converge to the minus Tracy-Vadim distribution. So Tracy-Vadim distribution is still the same thing, the first point in the area point process, and you converge to minus this thing. Well, in principle, in the first particle in the area point process, it might be both positive and negative.
So what it says is that this RT is
Not exactly, because the particles will, there is no identification for the next particle. It's not true. This is only about the first particle. Yeah, that is only.
What does it mean? X, T, alpha of T?
So this is a position of particle number t to the alpha at time t. So you can say that
It's not the largest.
yes, not the largest. So alpha should be arbitrary thing greater than 1.
So it's always this Vadim even for not the largest, which is surprising.
so that means the other constants depend on our.
Yes, of course. Let's write it more explicitly. So this is, of course, everything depends on alpha here.
So I thought that from the previous example you have some area for the process and this Vadim for the first one.
Well, in a second we will see that that's not a good point of view. So really, the correct point of view is that this alpha, that is precisely the same alpha that we had before. So this alpha really encodes position in your Aztec diamond, not the number of particles. So let me describe how it works. So, so my proof will be a little bit different from what Johansson explains. So I will give you another one. So it will be, I don't have time for full proof. I will give you a sketch. So the idea, as I told you, is to make a coupling. And in this case, we will just make a coupling to our Aztec diamond. Now, there is some stochastic system, and there is also a very nice stochastic system for the Aztec diamond. So let me briefly explain how this stochastic system is constructed. So remember that we identified the Aztec diamond with the trajectory of the Schur process. So you go up, down, up, down, up, down, maybe up, down. And the up steps that will be alpha specializations and down steps are beta specializations. And remember that we have a very nice procedure when working with the Schur processes. We kind of knew how to flip arrows. That was our skew Cauchy identity, where the summation over up down was turning into summation over down up. So let's first draw it schematically, and then I will explain what I want to say by that. So let's draw another row. And we will switch alphas and betas here. So it will be beta, alpha, beta, alpha, beta, alpha, beta, alpha. So one important corollary of their skew Cauchy identity is that if you consider the Schur process of y things, like going up and down according to alpha and beta specialization, and the Schur process of the yellow things, like going up and down here, down, up, yeah. Then the joint law of the vertices on their intersection, so these yellow ones, so joint law of yellow is the same in both options. So if you go along this thing and then you integrate out these vertices and you look at the joint law of this thing, then this joint law is just the same as if you go here and you integrate out these vertices. And the reason for that is just Q-Cauchy identity, because really to integrate out these things, you just need to sum over these things, and then that's precisely Q-Cauchy, which tell you that sum over this thing is the same as sum over this thing. So this is Q-Cauchy. Okay, now after you make this observation, you can make another observation, namely, if you start with the empty Young diagram and then you go down, then this is an empty Young diagram again, because there is nothing smaller. So this is an empty Young diagram again, and that's an empty Young diagram again. Okay, at this point you can realize that this part of your picture is another odd-stick diamond. And if you here started with a size n odd-stick diamond, then this precisely corresponds to a size n minus 1 odd-stick diamond. Okay? Now, given all these observations, here is an inductive perfect sampling algorithm for the odd-stick diamond. So let's do the following. Suppose that we have already sampled odd-stick diamond of size n minus 1, like this blue one. Then you take out of it all the yellow vertices, like these ones, and then you just resample these guys according to the distribution given by this alpha beta. So you think about 1, 2, these 3 points as forming a 2 times Markov chain, and then you resample this point out of the conditional distribution of this guy given these 2 guys. So given size n odd-stick diamond, odd-stick, you forget about these blue guys, about blue, and then resample whites. So this gives you a Markov chain which turns uniformly random domino tiling of the size n minus 1 odd-stick diamond to the uniformly random domino tiling of the size n odd-stick diamond. Now, if you remember, Alexey Bufetov was doing something similar when he was speaking about RSK. However, there is this important difference. Now, really, in the RSK, he wanted to preserve as much information as possible. So he was constructing this white vertex, taking lots of information out of the blue one. That is what is RSK. So RSK, preserve information. Now what I suggest here is instead of get rid of all the information, really just forget about these blue ones and you resample white ones. So we do forget information. Okay, so if you now, well, it remains to decode, of course, because you need to understand what does it mean to resample here. So it takes not significant efforts, but it takes some time just to write down carefully all the formulas. The result has a name. It's called shuffling algorithm for the odd-stick diamond. When people first discovered it, they discovered it through completely different argument, but still.
Shuffling algorithm is the first one, the RSK.
No, shuffling algorithm is this one. No, RSK will give you completely different sampling.
It'll give you shuffling algorithm with minimal amount of randomness. So you only need n plus 1 choose 2 bits to.
Yes, but it is. Okay. Like the thing that is called shuffling algorithm, there is the first articles of Elkis, Larsen, Cooper-Gerk, and Prof about odd-stick diamond, and what they call their shuffling algorithm. This is this thing.
Yes. Okay.
I mean, that is a question of terminology. You can say, okay, different one, let's call it also shuffling algorithm. That's true. You can do it, but canonical one is this one, not RSK, but this one on top. Okay, now let me just tell you what's happening in terms of the particles. So remember, we will identify an Aztec diamond with some particles. Now, if you rewrite these dynamics just in terms of this particle, there are some rules according to which the particles jump to the right. So essentially, particles just kind of jump to the right independently, but then there are some rules how they preserve all the combinatorial constraints in this picture. And in particular, if you look carefully in this room, then what you find out is that when you look at this part of the picture of the leftmost particles, then this precisely becomes this discrete time tacit. Yes, so shuffling tells you that you have a particle configuration, and then all these particles move a little bit, and then another row is added on top, is appended on top. So if you look here, the phenomenon is also here, because if you think about the particle which is distance n to the left, it doesn't move until the time n. There is just no way how it moved. Yeah. Well, there is some check, of course, that this construction gives you this discrete time tacit. I don't have time to do it, but that's what it is here. Because of that, now the theorem of Johansson becomes just a corollary of the statement that we have just proven. Because now the distribution of fixed particle is precisely the border of the frozen region. And because of that, the meaning of alpha there is the same alpha here, like this k, like k over n. Now the last question is, why is there a minus in that Tracy-Vadim distribution? So why is there a minus? Yes, kind of, because you look here, these are the smallest particles really. And here we had a limit for the largest particles. So the smallest turned into largest by flip. And that's why you get minus there. Okay, so that's how it works for discrete time tacit. Yes, that's true. Well, it's not quite true. So it's both true and untrue, because what is true here is that there is conditional uniformity. So at each time in this tacit, the measure that you give will still have conditional uniformity, like given the top row is conditional uniform. So if you know this conditional uniformity, then given the law of this thing, you can kind of reconstruct this thing. It's unclear. Yes, you add randomness, that's true.
No, the history of Tazak is not enough to get you
No, not enough. No, not enough. It's different in these dynamics that Dan was mentioning. So there is another one through RSK, then probably there'll be enough information. So in RSK dynamics for the Aztec diamond, probably it's enough to study one edge. Yeah, it should be enough to study one edge to get the entire thing. If you want several leading particles, then you need to go here in the Aztec, you need to go in this direction, kind of two levels, this one and the next one. As we just were discussing with Andrea, it's possible to do that. But no, it will lead from this. It will lead kind of to the extension of this Airy process. But yes, exactly. If you look at the several of the largest eigenvalues of the corners. Yes. Oh, yeah. In this sense, that's true. That's what the limit is. Okay, so can I go to the next example, or are there any questions about this one? Okay, so let's go to the next one. Okay, so for the next one, we take a permutation sigma. So let's take some permutation, maybe 1, 4, 5, 2, 3, 6. This is one possible permutation. Then we make a longest increasing subsequence in this permutation.
I had a question on the previous example. So the previous example, the coupling only works asymptotically?
No, that's exact coupling. That's exact coupling. So just at each time moment, the distribution of T-sep is the same as the distribution of the particles in this Aztec diamond. Well, there were two articles. I mean, no. I mean, if you look at the shuffling algorithm, it's kind of clear there that there is a discrete T-sep at the edge. So even in there, so the guys who first found the frozen circle in their Aztec diamond, I think there were several groups of people. Maybe it was Kohn, Jokush, and Prop, or something like that. So they actually looked through the T-sep. They didn't know anything about the Aztec diamond. They found this identification with T-sep, not through my method, but through different method. And then they used the hydrodynamic for the T-sep in order to obtain that there is a frozen circle there. But at that moment, nobody knew how to analyze, Aztec diamond in these details. Then it was Johansson who understood how to analyze Aztec diamond in details, essentially linking it to Schur measures, maybe in different language. And then it also became a theorem for the T-sep, for discrete time T-sep automatically. This picture, that was, that point was, there were two articles, one by Eric Nordenstam and another almost simultaneously by Alexey Borodin and Patrick Ferrari, where this point of view was advertised. Okay, so if you take now a permutation and you look at the longest increasing subsequence of this permutation. So what is the longest increasing subsequence of this permutation? So I think that for this one it should be 1, 2, 3, 6. And the length of this longest increasing subsequence, that is something that we'll call L. So the length is equal to 4 now. So about these longest increasing subsequences, there is a theorem. Well, first study of these longest increasing subsequences, that was a topic of study for many years. It was called Ulam's problem, because Ulam was one of the first persons who asked, what's happening if you sample your permutation uniformly at random? Then you look at the longest increasing subsequence of this thing. So what is it? How the asymptotic looks like? Then there was a Kammersley who made some progress. So there were many things that was Vershik and Kerov who did further progress. So the final result is due to Baek, Dave, and Johansson. Which tells that, so if you take sigma uniformly, and you call L of sigma Ln, where n is the size of your permutation, then limit as n goes to infinity of Ln minus twice square root of n divided by n to the 1 over 6 is equal to the trace-Vadim distribution. So that's a theorem of Baek, Dave, and Johansson. So you shouldn't be surprised by the scalings because really, if you have you should think about square root of n as the size of the system in a sense, as we will see in a second why that's happening. So the argument which I will now present is probably due to Akunkov. So he was the person who invited Schur measures, and because of that, this argument became clear at that point. So here's the proof. So what do we know how to do with permutations? One thing that Alexey was speaking for several lectures, so that you do RSK on permutations. If you apply Robinson-Shenstein algorithm to a permutation, then what you get is a Young diagram. Well, two standard Young tableaux, if you want to be exact, but in particular, you get a Young diagram as a common shape of these two Young tableaux. Now, the beauty of the RSK is that the length of the longest increasing subsequence is mapped to the length of the first row in this Young diagram. And moreover, if you look at the uniform measure,
This should be called RS.
I agree. And maybe even Shenstein only. Maybe. Oh. Okay. So if you look at the uniform measure, then, well, it maps to the measure which is called Plancherel measure, which is that probability of lambda is dimension squared of lambda divided by n factorial, where dimension is just number of the standard Young tableau of shape lambda. So, well, now it means that now you need to study this measure. Now, studying this measure is still pretty hard. Then there is another trick, which actually Hammersley was the first one to introduce it, which says, okay, so let's also make this n to be random as well. So make the n, random with the probability of obtaining any given thing being exponent to the minus theta times theta to the n divided by n factorial. In other words, now you have Poisson distribution with parameter theta, and you say, let's sample our n from the Poisson distribution with parameter theta, and then after we sampled n, we do the same procedure and we sample the length of the longest increasing subsequence. Well, for the Poisson, we have law of large numbers, which says that approximately theta will be close to n when both of them are large. So this can be made rigorous. I will not go into that. I will just replace deterministic n by random n given that. This is called Poissonization. What? So theta is close to n when both of them are large. So this is the law of large numbers for the Poisson distribution. If you think about n as being a random outcome, so if you take Poisson random variable with parameter theta and you call this result of the outcome n, then n will be close to theta when theta is large. So this is law of large numbers for these guys, nothing else. Well, if you do this Poissonization, then what's happening with this measure? Well, now you will have a new measure, p theta of lambda, which will be equal to e to the minus theta, theta to the n, times dimension lambda divided by n factorial squared. Now, luckily, this turns out to be precisely a Schur measure. So this is proportional to the Schur function of, let's call it p, let's call it rho square root of theta times Schur function of rho square root of theta, where rho square root of theta is the following specialization. So that's a specialization of the algebra of symmetric function which maps the first power sum p1 into square root of theta, and all other power sums pk are mapped to 0. So it turns out that if you apply this specialization to your Schur functions, then you get precisely this dimension divided by n factorial. And then there will be this theta of n appearing from this square root of theta. E to the minus theta, that will be a kind of right-hand side of the Cauchy identity. So this is a product of two of these square root of thetas. Okay, well, if this is a Schur measure, then we again have double contour integral, and we can repeat exactly word by word the argument that we just did. The only thing that will change will that this function g will be a little bit different, but still there will be a tuning of parameters which creates a double critical point for this function, and then you deform the contour there. You do all the same word by word, and then you get this theorem as an outcome. So then you play the same game. So that's how you prove this one. Yes, that's true. That's true. It tells you about several rows of these Plancherel random Young diagrams. So this was, there was a group of people like there was.
You get generic kernel in the limit.
Yes. Yes. You get every kernel in the limit for the several first rows of the Young diagram distributed according to the Plancherel measure. That's true. Okay, so that's the second example. So any questions about second example? Otherwise, I will go to the third example. No questions? Okay. So let me erase everything again. So the third example is actually much newer because all these theorems, well, they're like almost like approximately 15 years ago. Now this.
Wait, short question. So this specialization on raw square root of theta is kind of weird. You have to imagine in terms of ordinary variables. What does it mean?
Well, you can think about it as a limit of ordinary specialization. So you can think about S lambda. You take large n variables, each of them is equal to square root of theta divided by n. There are n of them, and then you send n to infinity.
That's just that.
Then this precisely will give you that afterwards.
Because
Well, P1 is deterministically square root of theta, and all other P's there will be n in denominator, and they will converge to 0.
okay, so this is one way of doing it.
Yeah.
So is it the case that all the Schur processes, maybe in the Thomas simplex or something, they will have
Yes, this area behavior, that's true. That is a very general thing. I mean, you can state very general theorem here that if the parameters on the Thomas simplex go to infinity in some nice way, then you always have convergence to Airy process somewhere. I mean, it's hard to state it in the more general thing because you need to make sure that everything converges in a nice sense because we needed to deform the contour, so we need to make sure there are no singularities which prohibit the deformation of the contours, etc., etc. Maybe because of that, I'm not sure whether anybody ever stated in the literature actually the theorem in this full generality. But in all the examples where people needed it, they will always manage to produce the asymptotic. Okay, so the last example is a result of the work of the last 3 years, I would say. It will be called stochastic six-vertex model. So how many people in the audience know something about the six-vertex model, at least definition? Okay, that's good. So in the six-vertex model, we have six types of vertices. And I will assign the weights to these six types of vertices in a very specific way. That will be 1, that will be 1, that will be B2, that will be 1 minus B2, that will be B1, that will be 1 minus B1. So everything will be defined given two numbers, B1 and B2, which are both between 0 and 1. Now, if you want to compare with the Aztec diamond, then the Aztec diamond also can be treated as a configuration of the 6-vertex model, but it is what's called free fermion point of the 6-vertex model. So in the usual parameter delta, which is used in the 6-vertex model, delta equals to 0. That is what corresponds to the Aztec diamond. So there is just a bijection between 6-vertex model and the domino tilings there. Yeah, I can tell you. So if you treat these numbers as A1, A2, B maybe is bad. Let's have A, large. A1, A2, B1, B2, C1, C2. No, they're not. Yeah, they're not. Shouldn't be like that. They should be with a symmetry. Yeah, it should be.
Yeah, I will make 1 minus
B1.
B2 and 1 minus B1 as the new B.
So that's the things. Is it correct? Yeah, are these traditional notations?
That one is it.
I think that's a traditional notation. Then you look at something like A1, A2 minus plus B1, B2 minus C1, C2 divided by twice square root A1, A2, B1, B2, something of this sort. And this is what's called delta usually in the 6-vertex model. Unless I, messed up with indices, which is very possible. So Aztec diamond also can be identified with the configuration of the 6-vertex model, and then you compute what delta you get, and you get 0 for the uniform measure of the Aztec diamond. Now here the situation is very different. These choices of parameters will imply that delta is actually greater than 1. So this is a different scenario. And because of that, the asymptotic behavior will also changed. Now, how do we define the model in more details? Well, if you think about Aztec diamond living in a quadrant, like in a square here, and really now the model will be infinite analog of that. So instead of square, now we'll have an octant, a quadrant. We'll have a quadrant, which is an infinite analog of this square. And there we will also have some boundary conditions. So we'll have a quadrant. So these will be positions for our vertices. And we will have incoming lines from the left. And we will have no incoming lines from bottom. After that, we will sample the configuration of our model recursively. So if you look at their coordinate x and y on this plane, yes, so it goes infinitely in that direction. And we will first sample the vertices. We will satisfy x plus y is equal to 1, so this one. Then we will sample x plus y is equal to 2, x plus y is equal to 3, etc. So we will sample it diagonal after diagonal in this direction. Now we sample it according to these weights, which I gave you there. So we start here. So you have one line from the left and one empty line from the bottom. Okay, you go to your configurations. There are not so many which match. Namely, there is only this one or this one. And luckily, they have two weights, B1 and 1 minus B1, which sum up to 1. So you can just flip a coin, biased coin, to choose with probability B1 this one and probability 1 minus B1 that one. Okay, so let's make some choice. So maybe we have chosen to go up. Okay, now you go to all the vertices here. So you look at the vertex here. Okay, we have no line here, no line here. We look here, we realize, okay, that's the only case which works here. And that has probability 1, good. So we use it. Okay, here we look, well, it's only case 2 which works. So we draw it. And etc. Then you repeat, like then you look here, you see that you have a line from the left and nothing from bottom. Well, that's again this case. So you choose according to these probabilities. Yeah. So what do we do to get another one? Yeah, exactly. So that's, no, if we continue the line, it will be the same.
Continue toward, like, continue the line.
If you continue straight.
Yeah, so we need to continue this way, maybe another time, and then maybe up, and then we'll have a choice of the different types. So if we kind of arrive from the bottom like that, then we are in this scenario, and then we again have B2 or 1 minus B2 to make a choice. So I claim that if you define the types of the vertices in this recurrent mode, like first on this diagonal, then on second diagonal, etc., then just combinatorics will tell you that at each step, either everything is deterministic, and you are in one of these cases, or you make a choice between these two cases, or you make a choice between these two cases. And you just flip a coin each time when you need to make these choices. And that is what we call stochastic six-vertex model. So it defines the distribution of the configuration in the quadrant. Okay, now you define the height function of this model. Height function. Well, by the definition, that is just a number of lines below your point. So maybe you are defining it here, so you go down. Okay, there is only one line, so the height function is equal to 1 here. And in general, for any point, you can define number of lines below it. Or if you don't want to count below, you can count to the right. This will be the same number. Just because of the geometry, every line will finally turn up at some point. Okay, so that's a height function.
You also count toward left.
No, either you count down or you count to the right. No, you don't have infinitely many because there are paths coming from the right and slowly going up. So when we go very far to the right, there are no lines there. Philippe, you asked something?
It's kind of plain partition.
Yes, kind of, but this is six-vertex model, so it's a little bit different. So in order to get
The function, the height function grows always this way and this way.
Yes.
No,
yeah,
so it's a kind of thing.
yeah, so it's a little combinatorics, a little bit different. Yeah. Well, it's the same combinatorics as in the odd-stick diamond. So if you think about height function of the odd-stick diamond, there the combinatorics is just the same. So here's the theorem, which first appeared in our article with Alexey Borodin and Ivan Gorin. Like 3 years ago. It says the following. So let's define function small h of x and y by the following formula. So this will be square root of x times 1 minus b1 minus square root of y 1 minus b2. You square it and you divide by b1 minus b2. 1 minus b1 divided by 1 minus b2 is smaller than y over x, smaller than 1 minus b2, 1 minus b1. It will be 0 if y over x is smaller than 1 minus b1 minus b2, and it will be x minus y if y over x, y minus x. If y over x is larger than 1 minus b2 divided by 1 minus b1. And I forgot to say that everywhere here we assume that b2 is smaller than b1. Now that is quite natural assumption that b2 is smaller because b1, if you look at the graph, it's kind of gives you probability to go to the right. Now b2 gives you probability to go up. Really you want to go more to the right than up because you already have many paths incoming from the left. So in order to avoid traffic jams, you want really to allow them to travel far to the right. So that's the reason for this restriction. B2 is smaller than B1. So then the theorem tells you that well, first, that the height function of the model at point Lx, Ly divided by L converges, well, to this guy for any x and y as L goes to infinity. And the second, so these two cases you really should treat as a frozen region. So because here everything is kind of not, very straight. So either you have 0, which means that you are far to the right and there are no paths there, or you get y minus x, which means that you are far up and there are paths everywhere. So this is really frozen, and this is really not frozen, just complete analogy with Aztec diamond. So if you are in that case, so if you have 1 minus b1 over 1 minus b2 is smaller than 1 over x, smaller than 1 minus b2 divided by 1 minus b1, then your height function, after you subtract from it the limit, L times h, x, and y, and you divide it by, well, there is some constant sigma of x and y, and then there is L to the 1/3, and then it converges to the minus Tracy-Widom distribution. Okay, so from the way the answer appears, you can see that, okay, it's somewhat similar to what we saw in the discrete TASEP, but there we also had minus Tracy-Widom distribution. Moreover, if you think more about it, then although there is since close relative to the Aztec diamond, as I told you, this differs just by the change of delta from the domino tilings, but you can see that the asymptotic behavior is completely different, because we know that in the Aztec diamond, when we were studying height function, that was about global fluctuations, and there we saw Gaussian free field. Now here, by some reason, instead of Gaussian free field, you see Tracy-Widom distribution. So the message is that delta is really important here, and we changed the delta and the asymptotic behavior of the system is completely changed.
The case where B1 is equal to B2?
No, I mean, any choice of B1 and B2 will result in delta greater than 1. So there is no way, I mean, you need to, yeah, there is no way to make it.
But this is for any y and x in that interval, right? It's
Yes.
not for extremal.
Yeah, that's for any. That's for any. So
You're at the edge of the limit check, like in the Aztec diamond.
yes. So it's kind of different. Well, we don't know multi-point fluctuations here. So there is really one-point theorem. Well, we can give conjectures, but the conjectures will tell you that it's really look more like a TASEP than like an Aztec diamond. So although it's a statistical mechanics model, but by some reason it behaves like an interacting particle system instead. Okay, so well, the behavior will change. I mean, it's probably analyzable, but the fluctuation is probably, so from the comparison with interacting particle system, this is kind of the case in KPZ universality class. Like beta 1 is equal to beta 2, this is what's called Edward Wilkinson universality class. That is kind of, if you think about SSEP, like a particle process where particles can jump both to the right and to the left with the same intensity, and they can block each other. And there is some Gaussian limit there. Although nobody looked at, people looked at it, but maybe not detailed enough, but it's known that usually there are Gaussian fluctuations. Okay, so how much do I have? Well, I have another 15 minutes, so let me sketch you very briefly. Well, I will not sketch you this proof. This proof original proof was quite complicated. I will sketch you a new proof, which appeared actually only last year or this year. It's not even appeared in print so far. So this new proof is combination of the articles of Bufetov and Matveyev and of Borodin. Okay, so what is this new proof? I don't want to erase it. Okay, in this new proof, you start by extending the notion of the Schur process by replacing Schur polynomials with something more complicated. Then we will want to replace them with whole Littlewood polynomials first and then Macdonald polynomials afterwards. So let's look at, it will be the first step. So you can define what is called Hall-Littlewood measure, which is really an analog of the Schur measure. But now instead of your Schur polynomials, you will consider Hall-Littlewood polynomials. And you don't need to know so far what is a Hall-Littlewood polynomial even. So just you have something called Hall-Littlewood measure. And you have two specializations. One is some equal number of A's, and other is some equal number of B's. And the theorem, which I believe Alexey told you at the end of the third lecture, was the following one, that if you look at this measure, and if you look at the lambda 1 prime, so you take your Young diagram and you take the length of the first column. Yeah, Hall-Littlewood. That's Hall-Littlewood, exactly. So if you look at the length of the first column in your Hall-Littlewood measure, then you got precisely, if this is x and this is y, the number of variables here and there, then you get precisely in distribution the height function at point x, y, and the identification of the parameters is as follows, that b1 is 1 minus ab divided 1 minus tab, and b2 is t times 1 minus ab divided by 1 minus tab, and t is a parameter of this Hall-Littlewood polynomial. So Hall-Littlewood polynomials, there are some symmetric polynomials which depend on additional parameter t, and that's the parameter which plays a role there. So there are several ways how you can prove this identity. So maybe if you think about this idea of coupling, then the most beautiful proof that you should think about it is that there is a version of RSK which works for Hall-Littlewood polynomials. Unfortunately, that's a part which is being written down at the moment by Bufetov and Matveev, but they promise to post it very soon. And this RSK shows you that just combinatorially, this RSK gives you the same as the stochastic six-vertex model. So just combinatorics turns out the same. Well, there are also now different ways to reprove this identity, but maybe that's not as exciting. Essentially, just because you can compute distribution here and there and then make sure, okay, they really coincide. But if you compute distribution, then maybe you're not so excited. Okay, so if you believe in this identity, then now the question is, okay, and how do you really analyze the first column in Hall-Littlewood measure? Now, the problem is that Hall-Littlewood measure is something more complicated than Schur measure. And a priori, there are no determinantal formulas, and so nobody knows how to analyze it. However, there is a trick, and this trick was kind of known before, but the first one to realize that actually helps in the problems like that was Alexey last summer. And the trick tells you the following. So the first, let us generalize even further and go to the Macdonald polynomials from Hall-Littlewood polynomials. So the Macdonald polynomials, they now depend on two parameters, q and t. One way to define them is by telling that if you take operator in n variables, like that. So this operator shifts the ith variable by q, multiplies by q, and then there is some rational factor there. And you act with it on the Macdonald polynomial, then you get Macdonald polynomial again, and there is an eigenvalue, which is sum of the q to the lambda I t to the n minus I. So that you can treat it as a definition of Macdonald polynomials. So these are symmetric polynomials which satisfy this. Now what is important for us is that you can upgrade it a little bit. So there are higher order operators which also work like that. So if you look at their sum over all the subsets of 1 to n, which have n elements, r elements, and you compute you produce the operator in a similar form. So let's have k elements. T to the k minus 1 over 2. Now product I belongs to I, j belongs to I complement, and then there will be again txi minus xj divided by xi minus xj. And then there will be a product I and I tqi. And then you apply to the Macdonald polynomial, then you get E function. So you get ek in the variables q to the lambda I, t to the n minus I multiplied by p lambda. Well, that's already a non-trivial property. So if you define your polynomial through the first property, then that's a theorem that the second property also holds. Well, so Jan Macdonald proved it. Now we're just using it. Okay. Now another thing which works with Macdonald polynomial is that they have a Cauchy identity which is very similar to what we had for the Schur functions. Namely, if you sum p lambda x1 xn times q lambda y1 y m, where q is the sum deformation of Macdonald polynomial, which is different from the original Macdonald polynomial by multiplication by an explicit constant. Again, we don't need it, so I will not write this explicit constant. Well, then the sum over all lambdas is equal to the product over I and j t xi yj q infinity divided by xi yj q infinity, where this is Q-Pochhammer symbol, which says that a q infinity is equal to 1 minus a times 1 minus qa, 1 minus q squared a, etc. So you multiply a by all the powers of q, and that's a convergent thing. Okay, so since there is a Cauchy identity, you can produce a Macdonald measure in the same way as before. P of lambda will be proportional to the p lambda of rho 1 times q lambda of rho 2, where rho 1 and rho 2 will be two specializations. Now, given this Macdonald measure, here's the proposition, which is a key to the asymptotic analysis of these things. So proposition. So originally, you can trace it to the work of Kirillov and Naomi and maybe Warnar, but in more algebraic framework. Of course, they didn't really cared about anything probabilistic. And in the probabilistic context, it was Alexey who noticed that. Well, it says that if you look at the Macdonald measure like that, and you take an expectation with respect to this Macdonald measure with some specializations, and the specializations suppose that you're just plugging in some variables. That's what we will need in the end. So the simplest possible specialization, let's have, I don't know, A1, AN, B1, Bm, and you take expectation of this Ek, q to the lambda I, t to the n minus I, then the thing does not depend on the choice of q. So does not depend on q. No, that's a theorem. That's a proposition.
No, I mean, these are the things that Vadim was telling me in
Well, partially, yes. Yes. He was mentioning that for sure. I mean, he was telling much more, but that was one part of that. Okay, well, actually, if you know, so you know, it's first it's a little bit surprising. Let's think about it. You know, the measure clearly depends on q, because the polynomials depend on q. The observable also clearly depends on q. Okay, here's a q. But somehow expectation of this observable does not depend on q. Okay, now how do you really prove it? Well, that's the same methodology that we had before, that the expectation of this guy can be written as an, if you call this operator dk, then it is dk applied to this kernel Let's call this kernel, I don't know, k. K is a bad thing, let's have this c. So it's dk over kernel c, then you divide it back by c, and then you plug in all your variables, a's and b's. Again, because of the eigenrelation, when you act by dk in your variables x, then precisely this ek will show up just by the eigenrelation. So that's the reason why that's true. Okay, now can we see the independence here? So if you apply operator dk, this one, to this thing, and then divide back by this thing, can you see that the result will not depend on q? Well, kind of. I mean, if you look here, there are no q's here at all. Q's are only here. Actually, if you look at this kernel, what's happening when you multiply it by q, so the argument is shifted by q, and when you divide back, then these infinite products will cancel out, and what remains will be something which no longer depends on q. Yeah, just the first term of the product, exactly. So it's kind of trivial observation. I mean, it's not trivial to make it, but you know, to check it, it is completely trivial. Okay, so how does it help? Well, you can make a corollary immediately. That that the function of the variable psi given by the expectation with respect to your Macdonald measure of the product of j greater than 0 of 1 plus psi q to the lambda n minus j c to the j divided by 1 plus psi t to the j again does not depend on q. Where I assume that this lambda n minus j, when the index becomes negative, then the lambda is plus infinity, so q to the lambda is equal to 0. So q to the lambda minus m is just equal to 0. Okay, well, this denominator, you should not care about it. Really, this is something that clearly does not depend on q. It's not a random thing. Now, numerator, essentially, this is just a combination of these guys, q to the lambda n minus j, t to the j. So if you expand it into power series in zeta, or in psi, then you get precisely the coefficients your EKs. So it's really a corollary of this thing that is written there. Okay, now you can specify this corollary to two cases. One is q equals to t. And if q equals to t, then the Macdonald polynomials, they turn into Schur polynomials. And then you get Schur measure. Well, if you have Schur measure, then essentially you repeat the same idea that we had with contour integrals, steepest descent analysis, and you get asymptotics of these guys. It will be just dominated by the edge. Well, on the other hand, there is also a case q equals to 0. Now, when you specify q equals to 0 in Macdonald polynomial, then what you get is precisely whole Littlewood polynomial. You can also specify q equals to 0 here. It's again very easy, because if lambda is positive, then setting q equals to 0, this will just disappear. So only those lambdas who are equal to 0 are important. And if you think about the number of the rows which are equal to 0, this is essentially just exactly the length of the first column. So this links you to your first column that we wanted to get, and more precisely you get the expectation with respect to the whole Littlewood measure of the product 1 over 1 plus psi times t lambda 1 prime plus g. Okay, now this lambda 1 prime is precisely the height function that we wanted to study. It means that now some strange observable of the height function, which is actually some q version or t version of the Laplace transform, turn out to be related to some simple observable of the Schur measure. And since we know everything about the Schur measures, since it's a determinable point process, we have contour integrals, we can analyze it however you like, we can obtain everything about this guy. And along this way, you know, you can reprove this theorem, which I mentioned to you in this way. So you can think this is again some kind of a coupling, because really we coupled 6 vertex model to the whole Littlewood measure, and then for this whole Littlewood measure we have even more to this observable. We noticed that even Q doesn't matter, and in the end we got the Schur measure, and then we analyzed it. And through this way, you get this result. Okay, so these are not the only systems which you can analyze. There are much more. There is a whole area, that's what we call integrable probability now, of the systems that you can analyze. Always, finding the system is always not easy. Because if you just take some random system, there is no reason why it will be analyzable. So you can think about it as reverse engineering, which we are doing over and over again. So we start with some algebraic framework, we know how to compute something, then we try to decode and understand, okay, maybe it's something interesting for some probabilities. And from time to time, we arrive at some interesting probability system, and then we can analyze it. And I think that's how the course stops. Yeah, so 1 minute overtime, so that's it. Thank you.